Hello, welcome to lecture 3.1. We're going to talk about some of the issues and ideas on how to do some initial exploration of the data before we get into deep analysis. So, for example, first of all, the how to prepare for a data science career. If you're a computer science major, I think there are a few things that we can look into. One is to write down the skills you have and think about which of the skills are the most important for you to develop and highlight in your resume. Do a search on a place like glassdoor.com to see how many pages of listings are there for those skills. And in fact, it's a good data science project. You can, for example, you can extract the HTML pages from the Glassdoor or any other job site and try to understand the tone of the advertisement. And also, if you want to beat the filtering websites, which seems to filter out before they even look at anything, what you can do is to create very different types of resumes and try those resumes with a different sort of emphasis on things, and you might have more luck. Again, there's no guarantee. It's an art more than a science, and you have to keep trying. So what's the plan today? We will try to understand data, and we will try to understand the types of data and data cleaning. So the next thing is to understand what we call EDA, or exploratory data analysis, and basic data visualizations, and we'll address some of the common data anomalies and how to fix them, and so on. So understanding data, first we'll discuss how to understand data. What does this mean? It can mean many things: the context of the data, who collected it, and is it complete, is it still valid? And there are many more questions that we'll try to look into. Why do we need to understand the data in the first place? If the data is not validated or understood, then it is dangerous to make conclusions about insights. Many people, in fact, jump into do analysis and make dangerous conclusions about data without a clear understanding of it. Good conclusions can only come from good understanding of your data first. So although it's not one of the things we like to do as a computer scientist, but it's something we really have to spend time on. We have to have a good understanding of the context of the data and what the data looks like and so on. So important questions to ask about the data is you have to ask the question, what's in this data? So the easiest way to find out about what's in the data set is to read the data for some subset of this data set into a data frame and inspect the column names and the data types. You should also look at the shape of the data. That can tell you the number of observations and the number of variables or columns in the data set. So when did this collection start? It is easy to find out from the website or by inspecting the CSV file. The date range for the data collected. Also, it is possible that some data might be missing. For example, the data collection service was down for 2 months, for example, and you might have missing data in the middle of the data file. How can we detect such missing ranges of data? So if the data is temporal, we can also plot the dates and maybe do a 1D plot to see if the things are missing, or just do a script on it and to understand things. So the most well-planned and coordinated data collections come from samples, and which is collected from a population. For example, when the federal government estimates the jobs created, then they have to do a sample and generate data to make the estimation. Now, this example we believe is a good representation of the population. For example, you create a sample that's a good unbiased sample of the population, and then you would enjoy using that data. And it's also possible that the data has come from a sample distribution. So you could have a simple normal distribution, which talks about a nice mean and a standard deviation, and but you might get this data. So there's a biasness built into the data from the beginning, assuming that this data come from a normal distribution. So instead of sort of getting the real data and understanding that it fits into a normal distribution, you could make the dangerous assumption that it is normally distributed. The next question you want to ask is that, is it sufficient data to answer the questions we want to find the answers to? So is it possible to make estimations or predictions based on the data sets we have? So our data science life cycle, there are a few things that we're going to be focused on here. One is that data creation. Data creation, we don't plan to create data because as data scientists, we find what we call found data. We find data, lots of data things that's available, and we try to extract insight from them. So we may not do data collection, but we need to worry about it if you think that there's something that you have to specifically design to collect data. For example, if you're working for a company, you might want to collect the number of times a customer click on a certain advertisement, and so on. So we have to ask some of the questions, like in the data creation, how is this data created, who created them, and is the data biased? How can we be confident that the data is a valid data, and so on. Data pre-processing is the one that we are focused on right now. We spend a lot of time on doing data pre-processing. In other words, we have to clean up the data by studying the variety of things within this data, which you will go through. The data analysis or pre-analysis, or the exploratory data analysis, we perform EDA by looking at the data more carefully. All right, so so in this data science cycle, we're going to focus on data processing and data analysis. That's what we're going to do. So data cleaning process, we hope in the future there'll be better tools to do data cleaning, because it's not fun to do data cleaning. And it's really the process of transforming raw data into provide subsequent analysis. So data cleaning often addresses the structure and formatting. In other words, we may have to remove some rows and columns, add rows and columns, format things to be more readable by maybe removing commas, or missing or corrupted values. This means that we want to find a way to identify the corrupted values, and we can eyeball the data set, we can missing, or we can remove the entries, replace with a zero, replace with mean, replace with a random distribution, and so on. So unit conversion is another thing. Oftentimes the data comes without any mention of units, and you have to pay attention to the context to understand the units of this data. If you don't care about the units, then it can create all kinds of problems in the visualization and the analysis. And encoding text as numbers, we can help represent them on a tree, for example. The good news is it's not rocket science, and bad news is data cleaning is a really big part of data. Okay, so the data cleaning and EDA cycle, it can be very long. In this case, we are doing EDA. In other words, EDA does not conclude anything. We might replace something with something else, and we might visualize two variables to understand how they look. We might plot 3 columns. So basically, you clean the data, you take a look at it, you clean the data, you take a look at it, until you're convinced that things are looking okay for any kind of deep analysis or serious analysis. So next we're going to take a look at the NYPD data set that can display some of the problems and issues and the solutions that we can find to clean up the data. Okay, so here we take a look at a Jupyter notebook, which does an NYPD data study. Now, this comes from a source in the city of New York. If you click on this link, you will see that where the data come from. So it comes from the NYC Open Data and gives you all kinds of records of what we call 311 service requests from 2001 to present. So, so the idea here is that 311 is more like the complaints that the neighbors make about certain things, some misdemeanors, and so on. So let's take a look at what we can do with it. So let's suppose that we have this data file downloaded. So let's say NYPD complaint data historic. This is about 256 megabytes, this file. This is really, in fact, these are the complaints that police officers did, and this file contains, which is really large, the complaints that the people filed through websites or calling. So if you, one of the things you want to do is that you want to understand how big is this file. So you can do stats on this file by importing OS and then doing OS stat on the file. And it says that it's 1.93 megabytes. So that's about 2 gigabytes. It's gigabytes, not megabytes. So it's about 2 gigabytes of data here. So it's very large. And it's not something that you want to open in your Jupyter notebook. This might never open, might take forever, and so on. So, but it's possible that you could open a few lines of code, a few lines of data to see something. So here, what we can do is we can open an input buffer. So obviously opening this buffer does not bring the data into the memory. And then we read 10 lines into the memory, into something called a line, and then we print the line from the memory. From that, we can understand some of the things about this data set. So it says some of the column names are unique key, created date, closed date, agency, agency name, and so on. So you can find out something about this data set and the first few records of this data set. You can know that the dates are in a certain format, the times are in a certain format, and so on. So now if you look at this file here, so one of the things you want to learn how to do is to think about how to break up a file. So for example, if you take about lines, maybe 100,000 lines per file, you can actually do the stats to see how things look. So you could do like a shape of the data set. So for example, if you read something into a data frame, the only problem here is you won't be able to read into a data frame because it's just too big. So here, what we can do is we can break the data into two small files. So here we define lines per file to be about 100,000. That's about 25 megabytes per file. And then we index the file. We say file 1, file range, length of the CSV file name, which is whatever the file name is. It could have like million lines of data. And then we say that if I lines per file equals 0, that means if once you get the first 100,000, let's do something, that you get the next 100,000, you do the something. So here, what we're going to do is just opening an original from the straight file system and then write lines to a new file with the index. So this actually creates a more manageable file. So if you actually look at the number of files in here, so if you look at data, you can see that several NYPD complaint files were created. These are more manageable than the ones before. So once we have that, then maybe we can open up the smaller file to do some sort of analysis. So here we could run, for instance, we can call the Python time function to get the time before it. So we can do an estimate of how long it takes to read a file of maybe 25 megabytes, and we can get the time at the beginning, time at the end. We can create the elapsed time, and actually it shows that in this case, it takes about 4 seconds to read 25 megabytes of data. So you can estimate, if you had like 100 megabytes or 1,000 megabytes, how long it's going to take. If you have a gigabyte file, how long it's going to take, you can do an estimation based on that. So it's very important if you create a data frame, then here, if you try to create a data frame, then you have to have an understanding of how long it's going to take. But this can give you, a smaller file can give you an idea of how long it's going to take. Right, so if you look at the head information, you could see all the column names, and it shows that there are 5 rows and 38 columns. If you look at the shape of the file, you can say it's about 400,000 lines of data, and then about 38 and so on. So this is I think this file is the NYPD complaint data file here. If you want to get, like, for example, some of the fields are here, latitude and longitude, and that gives you the location of this crime. So we can map the data into another data frame just by selecting latitude and longitude, and we can maybe do a scatter plot or whatever you want to do with that. So we can also do a variety of things. We can find out what each column means and so on. So if you create, like, for example, if you create a data from a smaller file, we can also try to understand in the data frame, when did the first 5 records, this is the first 5 records, so you can look at the beginning, the end date, and this is the beginning date, that's the last 5 records, and so on. So there are a lot of other questions you can ask, and you can even plot data on a Google map. We'll talk about that sometime to show you once you have longitude and longitude and latitude. Once you have the 2 coordinates, the latitude and longitude, then you could do a variety of things. All right, so let's move on to the lecture. So continuing to talk about exploratory data analysis, it is like detective work. In fact, Tukey, who was a professor at Princeton, he was a statistician, and he was the first one to think data as a science. So in other words, he was thinking we want to find some patterns from this data, and this is what scientists do. They collect data, see if they can discover something. So in the early days of statistics, the more focus was on theory, hypothesis testing, C-tests, T-tests, sampling, regression, etc. But the data samples were small and hard to collect. Those days, statistics is like we have to test a hypothesis, collect data, and analyze to see if the hypothesis is right with a level of confidence. Now we have this, what we call quote-unquote found data that come for free. So we have to clean it, but we can combine the found data and the collected data to get great insights. So long before everyone started talking about big data or the data science, the Tukey didn't have big data, but he was thinking about data science. He was thinking about data as more of something that we have to carefully look at and to do analysis and look for those things that we believe are not there, as well as those things that we believe to be there. So that's a great thing to keep in mind. So EDA is not about getting to know the data. So for example, you have to transform the data. That means convert the data from one form to another. In other words, we could remove some things, we could add some things, and so on. We could merge some things. We want to visualize the data to understand the data in a maybe 1, 2, 3-dimensional features at a time. Or maybe we can plot pairs of things to see how they relate. We want to summarize the data, so we want to find summary statistics to see if you can understand something about the data. So the potential issues in data are the things like missing values, missing periods, unidentified symbol, and so on. So this type of data, it's very important data analysis, is because it will inform the subsequent analysis, but it can help you discover hypotheses, but you have to be careful. So EDA is an open-ended analysis. You want to be willing to find something surprising, essentially. So here are some surprise findings during EDA. It says Walmart sales data reveals that Pop-Tart sales increase 7-fold sometimes. In fact, they found out that there was a hurricane coming and people stock up non-perishable food, and maybe Walmart can anticipate stockings based on this kind of weather events. And those who write with proper capitalization are creditworthy. So those who take time to properly do it, hence are more careful with all the other aspects, and including debt payments, and therefore they can be creditworthy. So a firm can encourage better writing in order to increase the chance of getting the loan. So an analysis, there seems to be a correlation with Uberites and high crimes. An analysis of the Facebook, in fact, this is kind of a weird one because this is in the San Francisco area. It's possible that the people who commit crimes get away in Uberites. That's possible, but we don't know for sure. If you like curly fries, you're likely to be smart. An analysis of the Facebook data on who like curly fries trace back to a smart person. By association, smart people have smart friends, and so Facebook can target people with higher education for curly fries ads. So if you're using Chrome or Firefox browser, you're more likely to be a better employee. That's because you have taken the time to download a different browser and configure it and so on. And so people know that you're curious or you're always trying to improve yourself. All right. So warning, all insights are just insights. They do not state anything for sure. But this can be used to get a business advantage if you understand certain things. Now, insights from data is very important. Now, we hear a lot in the news about how much stock exchange has done under the current president or previous president. But if you really plot the data from the beginning of their time in the office and look at the curves, you can see that in the Trump, there's about 19% increment in the value of the stocks since he took office. That's about 9.5% return. On the other hand, Obama has 182%. Obviously, he benefited from Bush's misfortune. And Reagan had the third highest curve so far. It's possible that Trump could exceed all of these people, but we don't know. We just have to wait either 4 years or 8 years to see what's going to happen. Now, key properties to consider in EDA is the structure. the shape of the data. So understanding the shape, whether it's a table, a vector, text file, an image, is important before EDA, because we might be asking different questions based on the shape. Granularity, how fine or coarse each datum is. So some data files are highly granular and some are less. If your problem requires more microanalysis of the situation, then granularity is critical. For example, in the Princeton Salon system, we record data every 5 seconds, but what can we possibly do with that? Maybe we can predict the behavior of a user and customize the reaction from the platform, but perhaps we could change the granularity to 10 seconds recording, which can save both space and time. So the scope of the data, how complete or incomplete the data, sometimes data can be incomplete. What are the possible cases? Maybe the data entry was interrupted during the shutdown. Maybe someone is looking at this data set 10 years from now, might wonder why that data is missing from December to January 2018, December to early January, where the government was shut down. So temporality, how is the data situated in time? Data changes all the time, so the validity of the data is critical. What are some of the examples of these things? You can think about that. Faithfulness, how well does the data capture reality? So random data do not reveal real behaviors, so you want to make sure that whatever the data you have is the real data. It's not some simulated or produced data. The types of data, there are two major types of data, the quantitative data and the categorical data. The quantitative means numbers with meaning of ratios or intervals. For example, you could have price, you could have a range of price, and they are both numbers at the end of those ranges. So with those numbers, we can do most of the algebra things. We could add, subtract, we could find the common area, common things. And so, for example, if you're going to look for the hotspots in the video where most people look at, you could look at each person's video session as an interval, and then find the intersection of all the intervals. So that's a good data structure problem that you could think of. On the categorical data, there are two types of data, the ordinal data and the nominal data. The ordinal data means they're the categories with orders, but no consistent meaning if magnitudes and intervals. Like, for example, if you say, rate this movie from 1 to 10, now you might think, well, okay, I'll give you 10, but is the difference between 10 and 9 and 9 and 8 is the same? No. We don't really think like that. We just give a number, and we don't really think through that. We don't try to compare those things. But there's some order. We know there's some order. There's a label, at least. That's an order. So, for example, preferences, level of education, and so on. The nominal categorical data are really categories with no specific ordering. So here you could really look at very simple operations for looking at the data in a specific order, but you really cannot sort or anything because we really don't know which one is bigger than the other one. They're not quantitative data. So structure the data. There are two types of big data files, the white data, which means that white data is 1,000 maybe observations, so each row is an observation, and maybe millions of variables. So each column is a variable, so you have a lot of variables and fewer observations. So we call the white data, so the file is white, it's still big. It's lots of variables and few data records. And the problem with this is that we might try to do an overfitting, and when you get new data rows, you may not be able to predict them correctly. On the other hand, the other types of files are long data, which means you could have millions of rows, so you have a lot of observations, and then you maybe have thousands of variables or features. So in this case, you have fewer variables, lots of data records. So all these things are very important for us to consider what type of things we want to apply to these type of data sets. That's very, very important. Then there's the tall and wide data. Then you have thousands and millions of variables and also millions of records. And so millions to billion samples. Some of the strategies for tall and wide data, oftentimes if you have tall and wide data, they are very sparse. Means if you take a row, we might have only a few things that are non-zero, the other ones don't exist. So when you have matrices or tables like that, we could use some techniques from the sparse matrices, which we will discuss in the course, to address those things. Or you could take subsample rows You can take a random collection of subsamples and do some analysis. Or you could do map reduce. We could map multiple rows into parts of this data set into multiple servers, process and reduce them. So the structure of the data is rectangular is what we prefer. We prefer rectangular data because the irregular structures are very easy to manipulate and analyze. So a big part of data cleaning is about transforming data to be more rectangular. So in other words, we always want to think about features, which are columns, and rows, those are the observations. So two kinds of rectangular data, the tables and matrices. So essentially tables are R Python, name column with different types. We can manipulate them, and matrices are numeric data, the same type. We will learn how to use linear algebra to do that. So let's take a look at multiple formats for representing data. Most common format is called the CSV file. That's the comma-separated values. Although it says comma-separated, it could be anything. It could be any delimiter that we can specify for CSV files. There's also the JSON file. Tab-separated and comma-separated are the same thing. You also have XML files that can be interestingly or useful. All right, so a very common format is the comma or tab-separated data file. Records are delimited by a new line. Fields are delimited by a comma or any other delimiter. And commas and tabs in fields, for example, if you have a comma within a field, the name field, you have to put them in quotations to avoid any kind of parsing that could create all kinds of problems there. JavaScript object notation, or what we call JSON, is a very common format these days. So when you make a server call, it could send you this kind of a JSON object, which contains a lot of information about the data that you get. In other words, rather than sending the data through a pipeline from database to the browser, you could send through a JSON object, and then the browser can display these things. It's a widely used file format for nested data. There's a natural map to Python dictionaries, many tools for loading JSON files. The issues with JSON files are each record can have different fields, and nesting means records can contain records and multiple records, and that can be very complicated. In fact, the IPython notebooks are represented as JSON notebooks. So in fact, we can open up one of them in a little bit. So the next one is the XML format, which is what we call the extended markup language, which has types. So you have a begin tab and the end tab. And you could have some sort of a tree structure represented here. XML, unlike JSON, is a markup language. It is somewhat similar to HTML. The only difference is that the XML only contains data with some labels on the data, and the styles need to be applied. On the other hand, HTML contains the styles themselves. You could have a bold tag or italic tag and so on. So XML gives you an easy way to define a structure for your content without having to define the style. And the style can be many different things. In other words, if you have the content in the XML format, you could produce the final output files for the phone or the tablet or the computer or any type of thing, or print and so on. The other common format of data is the server log data, which contains, like, every time you visit the server, it will record your IP address and where you came from, maybe your user ID and other things. And that can be very helpful. So, for example, typical system administrator may look at the server logs only when something bad happens, but how else can we use it? You might use the server logs if there's a way to. These are big data files, because a lot of server logs, every time you log in and log out, it makes a record of it. And these files can be very important. Like, for example, you can ask questions like, what the system down today, who was on the system on a particular date, and so on. So when you do forensics on digital files, you do look at server data to see where you were and what you were doing and those kind of things. The structure, the other structure is the keys. Open data will reference other pieces of data. So you might have a primary key in a data set, the column or set of columns in a table that determine the values of the remaining columns. So for example, you could have a table called customers.csv, which has customer ID as the primary key. So using this custom ID, you might be able to join these two tables and get some of the things like order numbers and so on. Foreign keys are the column or sets of columns that reference primary keys in other tables. So once you have a primary key, you could find the key matching in another table, which we call foreign key. So you could merge, for example, customer CSV and the order CSV. So databases do these kind of operations very commonly across tables and so on. Granularity, one of the big issues major issue in big data is that the data can be split across multiple files or servers. So you could have multiple servers serving your organization, and each server can have log files and other kinds of files that is important for your organization. So data can be very large and split across multiple files or multiple servers. So one of the things you do is the merging and joining tables, which you have specific commands in Python to do it and pandas to do it. So you could join two tables. For example, here we could join these two tables by the order ID. You have a left key, which is order number. We say is the same as order ID, and then we will try to match things. And if they don't match, we will just remove those dropped rows that don't match on the key. There are other issues associated with dropping things, but sometimes if you drop maybe a lower percentage of the rows, it can be okay. So it depends on how much you're going to drop. Data granularity can go from the context. For example, raw media data elements are very much like, for example, you record each person's video activity every 5 seconds. So you have all these bunch of data that has no structure at all. And then from raw data, you could create information object. You could group some data into some information object to provide a little bit more context to it. And then once you put together those information object, you could create what we call a learning object, which is a related set of things that are going around some specific center here. And then you could find these learning objects to create lesson units. So you could have learning objects and lesson units here. And then once you aggregate into a collection, so you could have collections of things. So in a typical course environment, this could become courses, stories, movies. So as you are in this side of the data cycle here, these things are more reusable. We could repurpose them for multiple uses. Once you go into this side, you get more context into it, and then you have already repurposed this into very specific patterns. In fact, you would understand that as we learn deep learning also goes through something like this. It just takes very raw data and, for example, pixels of an image, and then try to identify the features and group the features, and then eventually identify the picture itself. So in a neural network, as your data moves from one layer to the other layer, that data can create more structure, and we will talk more about those things as we get there. So key things to consider in granularity is that what does each record represent? Example, is it a purchase, a person, a group of users? Do all records capture granularity at the same level? So for example, some data could include summary, some data could include raw data. Or if the data was coarse, or how was it aggregated? Was it sampled, or was it averaged, and so on? What kinds of aggregation is possible, desirable, from individual people to demographic groups, from individual events to totals across time or regions, hierarchies, countries, cities, states, and so on. So understanding and manipulating granularity can help reveal patterns. So scope of the data. The scope of the data is, you want to ask the question, does my data accurately represent what I want to study? So for example, I want to understand crime and poverty in New York or New Jersey, but I only have data about New Brunswick. So is that good enough for me to inference the crime and poverty in the New Jersey area? Is my data too expansive? For example, if you have the salaries for Rutgers employees, but I only have data from the state of New Jersey, we could filter them to find the salaries of Rutgers people. If the data is the sample, it may have poor coverage. So it could be biased, it could be poor coverage. Is my data current to cover the right time frame? That's also very important. Sometimes the old data is no use, it's out of scope, and therefore it's not good to do analysis on. Temporality, key issues are the data changes, often when was the data collected, what is the meaning of a time and data fields, when did the event happen, when the data was collected or was entered into the system, the data was copied into the database, and then time depends on where. You want to look at time zones and daylight savings and other kinds of things. We should be able to use the datetime Python library to do many of these things. For example, most of the time the data is represented as in this format here. We might be able to extract a lot of different things. Are there strange null values? For example, does the data contain something like 13? There's no year 13, we know that, or month 13, I guess we know that. So that's the key thing. So there's also the time issues, the time measured in seconds since January 1, 1970. So you want to think about the regions and where the data is looked at. So there are a lot of other things that you want to incorporate into your analysis when you think about different data sets and different data time zones and so on. So it is very important that the dynamic modeling of data, because the data changes all the time. So the model changes also and evolves as the more data comes. So you learn a data, you learn a model, but the new data comes and then you change the model. You update the model, hopefully the model becomes more refined and more accurate. So it's a relatively new area of research, and there's not a lot going on yet, but people are very interested in understanding dynamic modeling of data as opposed to static modeling of data. So faithfulness, how well does the data capture reality? So do I trust this data? Does my data contain unrealistic or incorrect values? Again, you must understand the context to know that. So some examples are dates in the future for events in the past, locations that don't exist, negative counts, misspellings of names, large outliers. Does my data violate obvious dependencies? For example, age and birthday don't match. For instance, if you think that the birthday age, if you know the birthday, if the age says 150 years, we know that's probably not right. So nobody's living. Usual guess would be birthday plus 80 years. That would be the range you're looking for the max. But you could have outliers, few outliers, not too many. Because the data entered by hand, so you could make spelling errors, fields shifted. The form requires fields and provide default values. The obvious signs of curb stoning or data falsification. Repeated names, fake-looking email addresses, repeated use of uncommon names and fields. The signs that your data may not be faithful, missing values, which means that what solution you can do is you can drop the records with missing values, implications in your sample. Or you could impute the missing values with a bias, your conclusion. Time zone, you could convert to a common time zone like UTC. Convert to the time zone of the location, useful in modeling behavior in a specific location. Duplicate records or fields, we can find out, identify, eliminate those things. Using a primary key, we could do that. If you assume that there's only one record, the primary key is unique and so on. Spelling errors, we could apply corrections or drop records not in a dictionary. Units are not specified or inconsistent for units from the data. Check values are reasonable ranges for the data. Truncated data, early Excel limits were like 65,000 rows. Now it's a little bit more. Be aware of consequence of analysis. How did the truncation affect sample? So that's the end of this unit, but we will talk more about finding data, visualization of data, cleaning data, and other things in the